All right. So let's restart. We have Stas Babak who will bring us to the core of the Bayesian realm. So let's start. Thank you, Stas, for continuing this lecture today. The floor is yours.
I want to see your eyes. Eyes. Okay, good. We can start. It's will be heavy lecture, so I will need your attention. I'll repeat what we said at the end of the first lecture, and it's we're starting Bayesian analysis of the data, and the most important part of it is that we have a prior. We have a prior, and likelihood now updates the prior. Our variables are random, and therefore we're trying to estimate sorry, I obviously did not wake up. Probability distribution function of our variables, of our parameters of our signal. Okay. We also want to apply Bayes' theorem to the models themselves. We want to compare models and try to understand which model, we can have several models, describes that data observations the best. And that's where we finished. This is the Bayes equality, and we said that it's very hard to estimate P of D, probability of data, and therefore we're just using unnormalized probability and taking their ratio. And that's what we will call Bayes factor. Yes. Thank you. Good. And also ratio of priors. And I don't know if Richard convinced you that there are any theories beyond GR which we seriously should take into account. But let's not offend people who are doing testing general relativity, which assuming that these priors are equal. Otherwise, they can go home and do nothing. But in general, you need to take into account that not all the models are equally good from the beginning. You have other experiments which tells you that GR is by far preferred theory of gravity compared to others, even though it has limitations and most likely it's not valid in some regions. Then, if you're saying that, if I'm telling you that Bayes factor is the quantity you need to use to compare different models, then you can say, so how I'm computing Bayes factor. I will tell you how to compute Bayes factor. Next question is, so I have Bayes factor equal 3. What do I say? What would be my decision making? That means that model 1 is better than model 0, or it's maybe better, or Bayes factor 100 or 1000. And here it starts very hand-waving base of part of the statistics. So there is no, strictly speaking, thresholds which you can apply and saying this model 1 is preferred over model 0. It's more or less up to you. However, the statisticians who came up with this table, which I'm giving you here, Jeffries, we already mentioned his name, Jeffries Pryor, Castle Raftery, and other two guys very clear, very similar to Jeffries. But basically, they're all saying that if Bayes factor equal to 1, it means that in this expression here, there is not much difference between model 1 and model 2. Of course, we can say we cannot decide. Data basically is not informative about which model is better. 1 or 2, 3 or 4, 1, 0 or 1. They're saying if Bayes factor goes to 10, something like this, it becomes moderate. Maybe we should seriously considering that one model is preferred over others. Between 10 and 30, it's what they call strong or good. Very strong, it's when it's reaching 100, and above 100, it's the saying. It's kind of conclusive that indeed model 1 is preferred over model 0, or model 2 preferred over model 1. And it is also here where sometimes Bayesian people start to suddenly remember frequentist approach. And they're saying, oh, but let's do a lot of simulations. And let's try to get distribution of Bayes factors when, let's say, noise only. And they have a distribution of Bayes factor, like we did before, distribution of Bayes factor under model 0, distribution of Bayes factor under model 1. And they're doing the same as Newman-Pearson did for frequencies, saying, oh, now I can put threshold, after which I can tell you that if a Bayes factor above this threshold, I can accept or reject given model. Bayes approach doesn't know anything about this. Bayes approach is basically a table over here. Nothing more, nothing less. But it is there where people trying to have some kind of more associate Bayes factor with the false detection, etc. Oh, there are two people. Can't I throw it at someone, one of them? No, wrong choice.
So question is this a distribution of the Bayes factor, or is it a distribution of the estimates of the Bayes factor?
It's always estimations, because it's very hardly ever where we can get exact value of Bayes factor. So it's at every time you need to estimate Bayes factor. So it's analytically the evaluation of Bayes factor is almost never possible.
Yeah, but the distribution okay, that is the distribution of the estimates of the Bayes factor.
Yes,
okay.
yes.
Who is the other one?
Sorry. In this picture of the Bayes factor, how is it punished to add more and more parameters to your model?
We will talk about this, exactly about this point in the next few slides, okay, where the punishment comes from. I mean, and it is. There is.
Was there one more question?
No, keep it. Right. Before we're going to Bayes factor, let's concentrate for a few slides on the single model and trying to see how to estimate posterior distribution for a given model. So we assumed a particular model gravitational wave signal, and we're trying to infer parameters of this gravitational wave signal from gravitational wave observations. And you already saw it before in a colorful way. So this is our posterior. This is our likelihood. It's probably one of the last time when I'm writing P for the likelihood, because I just want to emphasize here once again Bayes equality. And that's a prior on the parameters given the model. If you choose different models, you might have different priors, and you might have at the end, or might not, different posterior. And so evaluation of this left-hand side is hardly ever again possible to do analytically. If it can be done, I know I would not give this lecture now. And therefore, we're trying to do numerically. What we're trying to do numerically is not to get analytic expression for this left-hand side. We're trying to get samples from this distribution. We're trying to, instead of knowing its explicit analytic form, we're trying to sample from this distribution, and then we will make mean or do whatever you want, maxima posteriori, etc. So you can do whatever you want with these samples. The idea is to get the samples. You can make histograms. I'll show you. And here we are using Markov chain Monte Carlo often. So Markov chain, we're always using first order Markov chain. It's a stochastic process which depends on on just previous point in the chain and nothing else. It doesn't have a history. So you're building a chain of the points in a parameter space. And you need to define what's called transitional probability going from one point in the parameter space to another one. And as you see, this t and t plus 1 means that it depends only on the previous state of the chain. And if you want to get samples from this distribution, then your transitional probability going from one point to another should satisfy this, what is called detailed balance equation. So that's your transitional probability going from one point to another. What it tells you that the chain should reach a stationary distribution, basically stationary state, okay, where going in time, let's say backwards or forward, is equivalent. So going from chain right to left or left to right, it's basically have the same probability. And then if you reach this state, then your chain should start sampling from this distribution. Now, I'll give you a particular case of MCMC building this transitional kernel. So we're talking about how to build now that thing, okay? And I'll give you both a little bit of theory, and then I'll give you example or algorithm how to build it, so it might help you. Even if you get lost in the math, I hope to get you back when I give a particular example or algorithm. Do this, and this. So first of all, in a Metropolis Hastings approach, you need to introduce proposal density. So it is really normalized thing. It's how to choose theta prime or theta t plus 1 next parameter in a chain given your previous state. It's totally in your hands, and I will comment on this, how to choose it and how dependence of your results on this choice. Second thing, you draw this new point from this proposal, and you build this ratio. That is called Metropolis Hastings ratio. It's the likelihood of the new point divided by likelihood of the old point. So again, you have likelihood ratio like we had in the frequentist approach. But it's not frequent, so you see this ratio of priors. If priors are not uniform, it does matter. So for example, if it's Gaussian, you might propose point from the tail of Gaussian, and it will be killed simply because of the ratio of the priors, not because of the likelihoods, which you would otherwise accept in a frequentist approach. And balancing this is an inverse, basically, jump from theta prime to theta and from theta to theta prime ratio of proposals. Now, if this ratio is larger than 1, you always accept new point. Just simply go there. You add this point in your chain. You're building the chain of the points in the parameter space. And this will be your basis of your posterior, basis of that. If it's less than 1, this ratio, this minimum here, it doesn't mean you reject it. It means you accept it with this probability. What it in practice means, you can draw another number from uniform distribution between 0 and 1. And if your ratio is larger than this random number, auxiliary number between 0 and 1, you accept it. If it is less, you reject it, and you assign to your new point your old one. You basically continue your chain, but you copy your previous state to the new one. I hope it's clear. Let's keep falling. And often I would suggest, if you're trying to do that, you do this not in terms of likelihood ratio, but you use logarithm of this. It's much more numerically stable. Because likelihoods could be large or very small numbers, and therefore, in order to avoid overflow, underflow, you should work with logarithms. So that is the very basic thing. That's how you build this. Okay, I'll let you write if you write. Okay. And I'm not going to show this, but just believe me that if you, basically what I want to say, detailed balance and your transitional kernel, which I showed before, it's this product of Q times alpha. This is this transitional probability which I have written here. And it satisfies detailed balance. Actually, it's quite easy to show. You simply substitute alpha explicitly in this expression, and you will see that it's satisfied. So, again, you will have these notes. You will have me speaking if you wish to hear it again. Let's move on. What I want to say is that your final result does not depend on choice of this function. You can choose this function any way you want, as long as it covers your prior, as long as it does not restrict your prior. Okay? Prior restricts your knowledge of the parameters, not the proposal. Proposal should cover completely the prior. But efficiency of your sample strongly depends on this choice. The best choice for this proposal is your posterior, which is kind of chicken egg. If you know this posterior, you would not need the proposal. But if you have a guess what, or some expectations, what your posterior could be, use it. What do I mean by efficiency? I will explain you in the next slide. So now I'll give you a few examples of kind of generic proposals which could work or might one way or another for any problem. The best, you need to build your own proposal based on your physical problem. If you know some symmetries, if you know some degeneracies, and also change of variables plays an important role. If you can change variables so that your posterior might be mostly Gaussian, that would be the best. If you know how to do these transformations to reduce the degeneracies or dependencies or covariances, that's the best. Anyway, one of the most popular proposals, random walk. You basically draw your new points from the normal distribution centered at the old point. And here the tricky part is to choose the covariance matrix for this multivariate normal distribution, Gaussian distribution. One of these choices, if you can know how to compute Fisher information matrix, compute it and use it as a sigma, basically. So it exploits a local curvature, but the disadvantage of this, it's basically monomodal. It stays in if you discover some mod, I will talk about these mods a bit later. It basically will stay there, but it's a very common, it's called random walk process. And moreover, because you see this proposal does not depend on the depends on the previous state, but in a way that it is symmetric. Okay, so going from theta to theta prime or theta prime to theta is actually the same. And so your Q ratio here cancels. And you end up with a metropolis ratio. Hastings added this thing. Next thing is that you just make completely independent on your previous state jump. Imagine you roughly know where you want to go, and you can simply draw from this distribution. One of the good examples, I don't know, Natalia, if she will speak to you about this. You might make a little run, discovery run. Then, for example, you can use neural network to make out of this proposal and draw it from there. Not as a prior, but proposal. If you expect some heavy tails, if you think your Gaussian is not very well approximated, you can use a student T distribution. Or if you know that there are some mods a priori, let's say in the LISA case, if you're looking at the massive black holes, I will show it again. There is a big degeneracy, okay? If you see merging massive black hole signal, this is a LISA constellation. If you have maximum, basically source coming from here, there will be a strong maximum mirror with respect to LISA's plane, okay? And if you found something here, you might want to try something there. And so you can right away build a proposal, which is mixture of two Gaussian at two locations of this. Back to here. No, give him a ball. Now.
Would that be more efficient to just redefine your, reparameterize it?
Yes. If you want, do it. Otherwise, if you're lazy,
okay.
then just to make a mixture of two Gaussian with equal probability. And another thing which works even better, mix them. So don't use a single proposal, use some mixture of proposals. And for example, you have a pool of proposals and assigned probability of each of them to be drawn randomly from this pool. Let's say 70% I will use random walk, 10% I will be using student T distribution, and global one I will be using another 10%, something like this, okay? And do it. I mean, this is the best strategy I can suggest you. Now, a few words about efficiency. Right, which one is this? This little example of data was simulated with a signal which is Gaussian, with sigma equal 1 and around 0, okay? And we're trying to sample from this, basically using Markov chain Monte Carlo, we're trying to sample from the posterior. We know what posterior should be. Posterior should be Gaussian distribution with 0 mean and variance 1. So basically, this is good. No, this is not very good chain. Which one is good one? That one is good one. So, because you don't know parameters of your posterior distribution, you need to accept that there will be some what is called burning period, okay? It's a period when the chain is exploring parameter space until it gets to the point of parameter space where its ergodicity or stationarity, steady state preserved, okay? And then at that point, you see it starts sampling and sampling something similar to Gaussian. If you just extract these points, you build the histogram, you will see it looks like Gaussian. So you need to dismiss beginning of your chain always. When you start dismissing, you can, most often you just need to judge by eye. You build your likelihood and you see when likelihood starts oscillating around some steady state. That's roughly where your chain already get to the state after which it starts sampling. Now, second thing, so it's burn in, and then acceptance rate. I said that you propose the jumps and then you either accept or reject them. What you want to have, it's a large acceptance rate. You want to, because otherwise you evaluate this ratio for nothing, again and again and again. If your acceptance rate is only 5%, it means out of 100 points you tried, you accept only 5 points. You waste a lot of computational resources. So you want acceptance rate to be relatively high. And here's an example when acceptance rate is very high. However, we know that it's a normal distribution with sigma equal 1. It needs to explore the range, let's say, even beyond 1. And it does this, but by tiny, tiny steps. So again, you fool yourself because acceptance rate is very high, but the points are highly correlated. So ideally, you would need to know to go in this range. But you're exploring this range by moving by little tiny steps. And how to see this? It's autocorrelation. Autocorrelation, it's basically you correlate data with itself with the shifts. And you see self-similarity. So it means that you're shifting by a little bit and you see the data didn't hardly change. So you take your chain, shift, correlate, and that's what you see this as. Of course, you can normalize correlation to 1 when you don't have any shift, and as a function of the shift, you see how this correlation evolves. You want black. You want that as soon as you shift it by a little bit, all the information of the memory is gone. Data is not correlated. They're not self-similar. Okay, it means that your points start to be independent. And the black one corresponds to this chain. Red one corresponds to this chain. Okay, so, and then you can compute effective number of samples. You take the length, for example, here length will be something of for the 200. So it's only 1 point out of 200 carries you information. You can as well just throw out 199 points. And you can compute effective number of samples. You take a number of total number of samples you have and divide by effective number of samples, which is given by, let's say, correlation 0.2, autocorrelation 0.2. This is what you can set as your autocorrelation length. And this is another example of bad chain. Again, it's a choice of your proposal. Here I use a proposal with a normal proposal with a sigma equal 0.1 instead of 1, okay? So indeed acceptance rate was high, but it's crawling. Chain is crawling to explore the parameter space. Here I use a proposal with a too large step. So sigma was 10 instead of 1. And you can see these flat regions, it indicates right away, it's a very poor acceptance rate. It means proposing points, they're way out of the range of my acceptance, and I'm staying at the same point again and again until I hit something new. So when you see this behavior, kind of steps in your chain, it means your steps way too high. Your proposal is not efficient in the meaning there are a lot of rejections. Yes, it does explore well the range, but again, number of points, these points are not 10 points, it's still 1 point, okay? So you need to choose proposal which A has relatively large acceptance rate and B has low autocorrelation. That's your aim. Now I'm coming to parallel tempering. Can you pass him?
I was just wondering, is there a reasonable way to set this sort of process so that like you were showing us options that have step sizes that are too small and step sizes too big, and you want to set it to a nice value, but could you also just have it sort of adjust on its own so it picks a nice step size?
Yes, you can do that. There is a problem with this. That's called adaptive Markov chain Monte Carlo, and very often people using adaptive chain Monte Carlo. So that basically the only way I said problem is you need to look at the past history of your chain, and that breaks the property of being Markov. It's not anymore Markov chain. I'll come to this, okay? And so there are two types of adaptation. The one adaptation which you start, you stop, you throw away everything was before, and just take points after you stopped adaptation. Second possibility is when adaptation dies out on its own. You still can adapt, keep adapting, but your adaptation basically will just fluctuate around, optimal value, and then chain is called asymptotically Markov, and it's almost Markov basically. Could you pass to?
Earlier, you mentioned that we can set the covariance matrix of our proposal based on the Fisher information. Can you say something more about this?
Yes. The only problem with this is the following. Okay.
I understood that would have answered his question too.
No.
At least, or no?
Not really. I mean, Fisher. Yes. Wherever Fisher information matrix is a reliable approximation to your likelihood. So you took the likelihood, you slice it here, you will have something like ellipsoid, okay? And Fisher gives you the eigenvalues and eigendirections of these ellipsoids, basically. It gives covariance of this. However, if your likelihood is not Gaussian, near the maximum, okay? You see that it's not, okay? There is a heavy tail. Then your Fisher will try to approximate it by Gaussian, and it might not be that great choice. You still should use it, but not rely only on this.
Okay.
Fisher information matrix for sigma is always a good thing to try, and it might or might not work. It's working more often than you think. So basically you do this. And that's your covariance, basically, matrix. However, it's a function of parameters. If you can do it fast, for example, if you can Jixify your waveform and take automatic differentiation of your H, of your signal, then it's a good choice, and you should try it, definitely.
There's another question.
Yeah.
Sorry, I'm not a data analyst, so very naive question, but what goes wrong when it's no longer Markovian? What breaks? Is it just the initial assumption and then? If it
breaks initial assumptions, you cannot guarantee that it will sample from your posterior distribution. So it could be biased.
Okay.
The way how it will be biased, it's hard to predict.
Yeah.
Do you mean to say we take the average Fisher? Because we don't know actually what the injection is. So do you want to just go
no,
through
you
the
can
whole
do it
prior space and evaluate the Fisher?
This sigma is not necessarily fixed. It also could be a function of theta in here. So you can recompute it again at each point of last point of the chain.
Ah, okay. Okay.
Then it's not symmetric anymore. Then if you take, then you need to balance it properly. Or you need to use an average Fisher in the region where you're staying and use it. As I mentioned, if you're just ignorant about your data and you want to stay within Bayesian approach, you start your chain somewhere in parameter space. It's not as your signal could be miles away from where you started it. That means that your burn-in time could be quite long. Nonetheless, you can still run your chains until it starts hitting something with a quite high likelihood. So in this case, your chain will be similar to your stochastic search, which we looked at the infrequentist approach. It will just random walk in parameter space until it starts seeing something. So it's not a solution, but that's how search is done in the Bayesian way. But there is a second problem which I mentioned, is this local maxima, okay? It's, you might hit not the global maximum here, but local maximum there. And the chain, yes, it can walk, descent, not only go up in the likelihood, but also go down. But if this, but if how to say, this hill is relatively high, it will not go all the way down. It will stop somewhere here, and it will not cross the valley. In principle, it can, but back to efficiency. It might take about Hubble time, so Chiara told you about Hubble time, to go from this maximum to this one. We need to help it a little bit. We don't have Hubble time to analyze the data. So there could be still a point accepted with probability 10 minus 30. It's not forbidden, but you need to wait for a long time. Instead, what you can do, you can heat your surface, what is called. So instead of likelihood, you compute likelihood, which is in the power of beta. And beta is 1 over temperature. It came really from the, because your likelihood looks like Maxwell distribution, and you adding temperature in the denominator looks like a temperature of in the distribution of speed of molecules in this room. And that's where it came heating and this analogy. And then if you, so what we need is a temperature equal to 1. Okay, this is your proper posteriors, that's your chain. With temperature larger than 1, if you look at the likelihood, this heated likelihood, instead of this one, it will look like that one. So each of these maximum getting spread and lower. And in this case, walking between two maxima is much easier. Okay, so my chain at this hot chain, what I call, with likelihood L to the power beta, can be easily moved back and forth in the parameter space. Of course, it will have more points here and there, but it will be jumping between two maxima. And the idea here is to run not one single chain, but n chains. N chains with different temperature. I'll tell you how to choose temperature in a second. And make them talk. So basically, hot temperatures will be just exploring parameter space at a large scale. And then they pass this information to the cold chains. And so now your cold chain through the hot chains will know about this one and that one. And if the maximum are equally or similar in height, your cold chain will start jumping between these two maxima because the interaction with the hot chains. So basically, a cold chain sees this picture, hot chain sees this picture, and they talk to each other. And they talk to each other again using Metropolis-Hastings ratio. And you take two chains with two different temperatures. Each chain has its own current parameters. And you switch parameters of the chains with this probability. It simplifies a lot when I'm writing in terms of logarithm, and if I'm assuming that the probability of swapping between different chains is equal. You can also add, of course, non-equal probability of switching, so swapping points between the chains, but usually it's not done. And swapping probability of being swapped is, again, defined by your ratio of likelihoods of different chains, and kind of weighted by difference in its temperatures. And this way, you can propagate information from hot chains to cold ones. And actually back, but back is less interesting in some sense. It is still interesting because you still do not you kind of return back from time to time hot chains where it should be, but it's less accurate anyway. And one of the good way of doing this swap, you divide your chains into odd and even numbers, and then swap odd with even in parallel way. So this kind of easily parallelized. So 0 chain with 1, 2 with 3, 4 with 5, etc. You can do one more swap if you want. Now you swap odd with even. Now, how do you choose temperatures? The best choice usually it's a geometric spacing. So based on this rule, okay? You want more chains near cold 1, whereas temperature equal 1. Because that's where your posterior lives, and you want to explore this region in vicinity of your true solution relatively well. Tmax. In principle, maximum temperature you should choose in such a way that it's sampling from the prior. So if you look at the posterior of your hot chains, it should be very close to prior. So this is the hot chain which doesn't see any maxima, any signals. So it just jumps all over. It carries no information whatsoever, but at least it gives you upper bound. If you see that your end chains above certain temperature, they're all returning you priors, you don't need this temperature. These temperatures are not useful. You need to reduce it. And one more thing is how you choose temperatures. It's you should aim at the swap rate, how often they swap with each other in a range between 20 and 60%. 40 is a good number. So number of temperatures in between 1 and maximum, try to achieve it by going to something like 0.4. And here you can also do adaptation. But then again, you probably should stop at some point if you want something. Actually, you don't need to. You don't need to, but if there are some cases in which you want to keep it. So,
the swap can occur in principle at any move, and at every move you accept the swap with a certain probability. Is this correct?
Do I have it?
Or do you try to swap only every n moves?
It's up to you.
Okay.
So you define probability of swap, parallel swap, and when you're doing regular proposals, after each proposal, let's say, I want swap with probability 50%. After each proposal point, I either accept or reject it using Metropolis-Hastings ratio. So I start with this one, okay? And then I'm drawing random number and comparing to 0.5. If it's above 0.5, I'll do parallel swap. If it's less, I'll continue with Metropolis-Hastings. Or you can swap every time. It's totally in your hands. You can see the parallel tempering as another very powerful proposal. And like any proposal, you can attach probability of being used. So why you can see it as a proposal? Because the hot chains proposing you points. It's not it's numerical way of proposing new points. But it is, you can completely see it as a yet another proposal.
So about choosing the hottest temperature, does it make any sense to take that hottest temperature to be infinite, so beta 0?
No. Unless you want to do parallel temporal thermostatic, thermodynamical integration. If you want to compute base factor, then you still don't want to go to infinity, but you want to go to a large number because it's your upper bound of your integration. And the question is how much you will get it. I'm not going to cover here, but you can get base factor by integrating average likelihood over all the chains. Usually it's quite unreliable, but you still can do it. And then you need to take care of Tmax more carefully. Yeah. So at the end of all of this, you will have something, set of points, which you can plot as a corner plot. So Jean-Baptiste asked me to show at least one picture of corner plot. It's two-dimensional marginalized. So basically you have, here I have 8 dimensions. And for each pair of dimensions, I'm plotting this 2D histogram and marginalized 1D. Okay? And here you can see some degeneracy in the parameter space. These are phases, these galactic binaries. It's a degeneracy between polarization and initial phase. And another thing which is I want to warn you and explain to you is that importance, if there are some variable like phi and you want to restrict it between 0 and 2 pi, it's better to let it go beyond 0 and 2 pi and wrap it up. And you can see this wrapping here happens, okay? These tails, it's a part of the part here, okay? This tail is a part of basically extending here. Why it is that? Because it correlates with other parameters. And if I didn't do this, I wouldn't have that. And this part actually propagates into here. So if you have periodic variables, it's better to extend the range and then wrap it up on your physical range between, let's say, 0 to pi or 0 pi. That's all what I want to show you here. And we're going to estimation of base factors. Now we will be talking about how to compare models. And the most straightforward way to compute base factors is to compute evidence. In other words, computing this integral. It's non-trivial. It's a multidimensional integral where we have just it's quite expensive to compute overall. And well, nonetheless, that's a still used method, and it's based on what is called nested approach. The basic of this is very simple. You start with your, you basically construct auxiliary quantity, which is x of lambda. And the lambda is basically integral of your prior over part of the parameter space such that your likelihood above certain value lambda. Absorb it. Okay. So basically it's a probability of L likelihood larger than lambda. And x goes between 0 and 1. Let me show you on this picture. We all know how to integrate function using Riemann method, okay? Basically, we're just taking delta x, small delta x, we compute y and this h delta x, and then we're doing this either trapezoidal rule or rectangular rule, whatever you want. What I'm showing you now, instead of doing vertical slicing, I will be slicing horizontally, like cake. And that's called Lebesgue way of computing the integral. The same, after all, exactly the same. So I'm splitting into roughly equal slices, and then I'm using either trapezoidal rule or rectangular rule, whatever you want. This method is basically this way of integration. Nothing more complicated. I'll tell you what this complication is. So, and then if you manage to compute this x of lambda, so basically it's slices of this cake going from 0 to, from 1 to 0. And then you simply integrate this x of lambda, which you empirically get between 0 and infinity, and you get the evidence. So this is the way of computing this integral. This is overall theory. Now let's see where the problem lies. It sounds very easy, right, to do. So I'm just slicing my prior and looking at likelihoods. It shouldn't be here. Now, to simplify your life a little bit, I'll give you algorithmic sketch, how you do this. in practice. You start with the endpoints completely randomly spread in your parameter space. They're called live points. And for each live point, you compute likelihood. And you start with zero value x0 equal 1. And we reduce x0 from 1 to 0. If we never reach 0, but we have to put some stopping conditions. When x is relatively small, we stop integration. And then you're doing iteration loop. First of all, you choose the point among all your live points such that the likelihood is the worst, the smallest likelihood. And then we're throwing this point away. This is called dead point now. We're putting in our pocket. And we want to draw another point. And we also need to attach weight to this point. And weight to this point is attached using going from xi minus 1 to xi with some auxiliary variable ti, which is usually drawn using this exponential and yes, basically using this exponential. We advance our computation of evidence by likelihood of that point times this weight. Okay? And as I said, we save this point, that point theta I, with this weight. This is needed for posterior distribution later on. It's not for integration, but if you want also to have posterior distributions, you can have it as well. This is good advantage of nested sampling. You have both integral and posteriors. And then you need to search for new point such that its likelihood is larger than points you just killed. So you basically evolve your points from you throwing the worst, you save it with some weight, and you're looking for a new point with a likelihood higher than what you just killed. Okay? So at the end, you also have termination conditions, which is given here. So basically, when you reach a value of xi close to 0, you think it's good enough for me, I'm stopping. Otherwise, you can go continuously on and on and on and on. And at the end, you will have your evidence with some error. You can also estimate error. And you have dead points which you saved in your pocket. But these dead points which you saved in your pocket have weights. So it's not done. It's not fully posterior. So it means that not all these points which you saved are good enough. Because some of them, in the beginning, they will have extremely low likelihood. And your weight gives you probability of these points, kind of weight of this, how much this point contributes to the posterior. If you're lazy, you can simply use a corner plot with the option weights. And it will plot you directly the samples, taking into account that weight of one point could be large, and other points weight is low. If you're not lazy, you can resample your points. So basically, one of the possibilities, you draw point from your pocket with a probability equal to its normalized weight. You take all the weights, normalize to 1. And so basically some points will be drawn more frequently and even several times. Other points will be drawn never. Okay? So that's how you get the posterior out of nested sampling. And you have also evaluation of integral. One of the advice is to map all your priors to uniform hypercube. Then it works much better. The hard part, as you probably already guessed, is how to choose new point. So basically, this requires, moreover, it should be, new point on a restricted prior. So basically, you're excluding some points out of your prior with a low likelihood. So you want to draw a point based on this condition. You want to draw a point from the prior with likelihood larger than certain value. There is no uniform solution to this, and that's a research which people doing, and there are different methods of doing this, like a dynasty, multi-nest, polychord, CP-nest, Nisei. They're all different in one thing: how you draw new point after you killed one. So you can read these papers. I'm not going into details what the particular implementation, but that's the idea, okay? So algorithm is rather straightforward. The hard part is here, 2.5. Once you know, you can compute evidence for each model which you want to consider, and then you take ratio of evidence and you will get base factors. What is the disadvantage of this? It's very expensive. Especially more dimensions you go, the harder it is. And moreover, you don't have the result until your integral converged. So you cannot even look at the partial result. Sometimes it takes you days or weeks until you get your posterior and final results. Compared to Markov chain Monte Carlo, you can stop it at any point, look at the results, and then continue it again from the last point, because it's a memory, it doesn't have memory. So starting from the last point of Markov chain is equivalent as starting from the beginning, and that's it. So now there are two other methods which trying to avoid computing this integral explicitly. One is a reversible jump Markov chain Monte Carlo, another is a product space. Of course, they're closely related, and to me, easier to understand product space, but I started with a reversible jump because it's more widely used. I'll try to explain to you basics of this, and then I'll give you one example. So here we're trying to do transdimensional Markov chain Monte Carlo using Metropolis Hastings. What does it mean? That we're jumping not only in the parameter space of a particular model, but we also jump between models. So our models, let's say we can attach to each of the models some kind of state, M. It's a 0 or 1. So either this model is active or it's not active. When it's active, it's used to compute likelihood, etc. When it's not active, it's completely ignored. And we need to, so now our target distribution, our posterior, it's not only parameters, but it's also model space. Which model is more likely? So this M, which is the state of the different models, becomes random variable. And you attach probability to each model to be able to describe our data. The advantage of this, I can look at many models at the same time. I can use only two models, or I can put say array of 3, 4, 5 models. Of course, it will be more expensive computationally, but I can try to have probability distribution between different models. So because I have at the end some kind of histogram on M, it tells me which of these models more or less likely. Is it clear at this point? Oh, I think I'm losing you. I'll start again. I introduced the model state, M. In a way, it basically tells you how often or this model particularly triggered or jump to this model was accepted or rejected, okay? And it gives you model state. In a way, it's 0 or 1, okay, for each model. It's either on, and then I'm using this particular model with this particular parameterization in my likelihood. When it's 0, I'm using other model which state 1, okay? And in the transdimensional extension of this, each M of each model could be either 0 or 1. But then I can, at the end, I will try to make a histogram of which model was triggered more often than others. The problem with transdimensional jumps is that different models could have different dimensionality. Let me give you, I'll give you a nested model example. And this is, you cannot do jumps between if you have not matching dimensionalities. And that's an ugly part of this, in my opinion. You need to create an auxiliary parameter u to make sure that dimensions of a particular model theta plus auxiliary u is matching dimension of another model with theta prime and u prime. And this should be kind of reversible mapping between theta u and theta prime u prime. And then it's the first thing which you need to do. So if you're trying to compare several models, you need to create these auxiliary variables to match dimensionality of different problems. Again, I'll show you an example, maybe you'll get a better idea. And then you also need to attach priors to different models, of course. And you need to have a probability of transition from one model to another. And matching of this auxiliary and true parameters, you will need also determinant, Jacobian of the determinant of this transformation. And once you put everything together, you have this Metropolis-Hastings acceptance ratio going from model M to model M prime. This model M will be characterized with parameter theta to model M prime characterized with parameter theta prime. So this ugly extension of Metropolis-Hastings, you see this Jacobian here. You see probability of going from one model to another. You see likelihood of two models. You see priors on the parameters from two models. You see probability of each model in this expression. And you basically see also, how to say, proposal going to this auxiliary variable u. Okay, so at equation number 24, my general description stops. And then I will considering more practical and often most useful one. When you have two models, models M0, which are parameterized by parameter theta, and model M1 parameterized by theta and psi. Theta here and here have the same meaning. Good example is model 0 is a noise only, parameterized with some parameters. Model 1 is noise plus signal. It could be model 0 is one gravitational wave signal, model 0 is one gravitational wave signal, model 1 is two gravitational wave signals of different types, for example. Or, for example, gravitational wave signal plus glitch. The key point is that theta are a common set of parameters. Again, I need to choose auxiliary variable. And the most natural way of this mapping is that because I need to map from this to that, and most natural way of mapping is u taking to be kind of psi way. Okay, so u prime I don't need because it has two. I have only add auxiliary conditions to this model to map to match dimensionality of model M1, and u is playing role of the kind of psi. So I need to choose some kind of proposal for this u given the model M0. And at the end, I have two possibilities. Birth, so going from model M0 to model M1. Birth means I'm adding extra parameters. Death, it means I'm killing. So for example, here, going from one gravitational wave signal to gravitational wave signal plus glitch, it's a birth. Going backwards is a death. And the birth one, the ratio, it's again the ratio of likelihoods, ratio of priors. Here is a theta phi, here is theta only. Ratio of models, probability of jumps, and this proposal. Basically, it's a question going from model with only theta to model theta and psi, you need to propose psi. It's completely in your hands, but you need to choose this. So to going from a parameter model which has only one gravitational wave signal to model with gravitational wave signal plus glitch, you need to choose parameters of your glitch, right? And you can see also that all dimensionalities will be matched and everything will be fine. But you still need to define this quantity. Sure.
This example, it looks like model 0 is nested within model 1.
Yes.
Wherein psi, whatever values of psi corresponds to glitch amplitude equal to 0 is model 0.
Yes.
So we have a natural, so can we not write psi, I mean, can we not just append that to M0?
This we'll try to avoid. So you can also try to estimate, because yes, it's a kind of how much the model 0 is collapsed to inside model 1 to a single value. And there is such evaluation called based on
Savage decay.
Savage decay, yes. Savage decay ratio, which is actually exactly does this. It's trying to evaluate base factor based on the fact that, model 0 is a kind of a bit tricky because it's 0 volume inside M1, so it's for a particular point. But it's usually it gives extremely unreliable evaluation.
I guess my question is, the extra parameters that we're going to add to model 0 so that the dimensionality matches M1, why not those extra parameters take values that correspond to glitchless or glitch amplitude equal to 0?
It can, but you want to explore your glitch, right? And so that you want to explore if model 1 could contain, basically saying there are two signals there, and you want to explore this model, so you should draw some value psi to go to this. So basically you're trying to saying now my model 1 will have parameters of signal, gravitational wave signal, and parameters of the glitch. If you always keep it 0, you go back to your original model. It doesn't help you. You want to draw it from something, to explore possibility to having glitch in addition to gravitational wave signal.
Okay, then I guess my question is, in model 0, what does it mean to have some random value of psi? It doesn't
make any. So for the model 0 psi, I even put here U explicitly, specifically, because it's auxiliary function. It doesn't have any meaning.
Okay.
And it's completely in your hands how you choose it.
Okay. This is just to match the dimensionality and just so that you can explore M1 space better.
Exactly.
Gotcha.
Exactly. And similarly, you can get for depth, going from model 1 to model 0. I'm not going to describe this, but now this Q function, which was in the denominator, appears in the numerator, okay? But the same happens here. You have likelihood ratio, you have ratio of priors, you have ratio of probabilities of different models, and you have this Q. In this example, the Jacobian is equal to 1. You can explicitly check, okay? And that's why it does not appear. And it's good to, let's just look at the one particular case when priors in model 1 decompose or factorize into the prior for, let's say, gravitational wave signal and prior for the glitch, assuming they're kind of independent. And in this case, you have again a ratio of likelihood, ratio of the priors of the probabilities of the models, but the important part is this one. That defines efficiency of your reversible jump Markov chain Monte Carlo. What it tells you. And that's where the penalty factor is. Who asked me about penalty factor? You asked me about penalty factor. Look at me. Yes, good. So that's where your penalty factor lives. One of the choice for this, how to propose this psi from model 0 to model 1. It's again, I said, it's completely in your hands. One of the choices, you draw it from the prior of psi. Okay? Then this cancels completely, and what you're left with is a ratio, assuming that probabilities others are the same. Model probability is the same. Going from one model to another is the same. You're left with the only likelihood ratio. If Q is equal, probability, I'm drawing from the prior. So where is the problem here? Where is the penalty factor? The penalty factor lies in the random draw from the prior. Try to find the signal inside your prior. If your prior is narrow enough, then basically this penalty is very weak, and you immediately will find the signal and everything is fine. If your signal volume, again back to what we talked before, occupies tiny fraction of your prior, and it's often the case, probability of drawing point from the prior and hitting the signal is close to 0. and higher dimensionality of the problem you have, the lower this probability, okay? And that's one way of looking at the penalty factor. This is called curse of dimensionality. Another way of saying, no, now I'm not so stupid, I'm not going to draw from the prior. I did, well, I don't know. Kanta told me, no, there is a glitch there at this time with roughly these parameters. And I will try to make this, how to say, proposal quite narrow. And so this ratio will be less than 1. And that's actually has to be compensated by increase in the likelihood. So if my tailored proposal for how to choose this parameter psi are very narrow compared to the prior, it has to be compensated by a large increase in the likelihood. And if glitch is weak, it's not going to happen. So the best way of proposing Q is actually have something in between. So not the prior, not very narrow tailored to the signal which might be there, but has something, prior, how to say, preference to parameters which I think are correct, but nonetheless, which would not kill right away the likelihoods. Because if my proposal is not very accurate but very narrow, it basically will kill this model. This is the state. This is the art of choosing this thing, okay? And your efficiency at the end will depend on this. You can choose a prior; it always will work, but you will need to wait for a long time for chains will give you something meaningful, okay? And here is a little sketch. So you have two jumps, okay? First of all, you need to do, again, probability of jump between different models, and you want to jump inside the models. And you introduce probability of each of them being triggered. You start your chain, and you probably want to have high probability to jump inside the model. So you're not changing the model. You're just doing Metropolis-Hastings step inside the model. Then once in a while, you trigger jump between the models, as we described before, like death or birth. And then you either accept or reject, and then you jump again a few times inside the model in which you're staying. So you have to alternate jumping inside the model, which explores a given model, with jumps between the models. Okay?
I didn't understand the Occam's factor part, the one above. How?
Try to repeat it and you will understand better. Try to repeat what I said.
I didn't understand what you just said.
Let's do it again. So you see this ratio of priors versus your proposal. The easiest one is choosing my proposal be equal to prior. Then it looks like this Occam razor disappears, which is not really, because it's still there. It's inside your prior. So if your prior is very wide, then going to extra dimensions is very hard. Basically, you need to hit your signal, high likelihood point, just by randomly drawing points from the prior. It's back to your question about psi equals 0. Now you extend from psi equals 0 to quite large range. It's not in one-dimensional, but many-dimensional one. So psi has dimensionality not one, but many. And therefore, by randomly drawing point in psi and hitting the high likelihood, it's not very efficient. We know that we're trying to make a search in our prior. It takes some time. By first randomly throwing the points inside your prior, you not necessarily hit. You might hit or you might not. But you will need to repeat this again and again and again. Even if you found the signal by chance, you will lose it in the next step. And then when you're trying to repeat again, you might not so easily find it. So it's back to the volume of your signal inside your prior. If your prior is narrow and you know that signal is there, then it simply will not be penalized very much. And that is also encoded in here now. If your prior is large, and you can keep it this way for physical reasons. Remember, you choose prior before you start looking at the data. And then you started looking at the data, you're saying, oh, I think there is a glitch there. So you started with a very broad prior to making sure that you're not losing glitch at all. Now you want to narrow down around where you think your glitch is. And now you end up with this ratio of your initial prior, which you started with a part of the parameter space where you think your glitch is. This ratio is less than 1. Because your prior is normalized, your Q is normalized.
Wait, shouldn't that be Q of psi given data?
No. It's
no.
Sorry, I'm talking about this, right?
Yeah.
No, it's completely in your hands. It does not depend on the data. It might or might not. As I said, one of the examples of Q is a prior. Prior does not depend on the data. So Q is in your hand. You can choose whatever you want. And if your prior is very broad and your choice of Q is very narrow, this will be quite a small number, and you need to compensate it by likelihood ratio. So you need to make sure that actually what you're proposing has a very high likelihood compared to gravitational wave signal only.
Sorry, last follow-up question is that, so that means QB, right, of that bottom term, it'll basically collapse in this glitch case. When you're conditioning it on theta and model 0, it'll basically collapse to the values of psi that correspond to zero glitch, because your model is M0.
No, it means that you do not have information from a model 1. You based your model. This basically saying that it does not depend on model 1. You might find that's exactly where you actually, again, switching on to frequencies. And you're trying to search your data for presence of the glitch, for example, or presence of another signal, or present signals in the noise. And then if you found something, how do you incorporate this information into the Bayesian approach? And the best way is to try to explore your glitch a little bit, try to understand what parameters it corresponds to, and then try to build a proposal around this. And the point is, in your frequencies approach, most likely you will search for the glitch without gravitational wave signal. So it will be biased, or some kind of your parameters will not be exactly what you want, and that's what you want to incorporate in your distribution. So you take Gaussian around frequencies parameters which you found, but not very narrow. Make it broad. Anyway, you need to cover by your proposal your prior. It cannot be narrow. So you cannot choose. That's your prior. You cannot choose proposal, which is basically it's a good bad example. You cannot choose Q like this, but you can choose Q. I'm losing it. Q like that. Okay, so that it also leaves you a bit of uncertainty in your frequency estimation of your psi, and it also not as severely has to be compensated by your likelihood. If you're a bit off and likelihood is not that high, it still could be accepted and then climbs up. I don't know if I explained or lost it completely. But basically, try to play with this, okay? And you will realize very soon that if you're taking Q from prior, it's hard to find. If you more tailor your Q, it's this balance between. If you know exactly where parameters is, you can make it very narrow. And then your likelihood will be compensating this small ratio. Right. I did say one more thing. Before I'm going next, yeah.
Very short question, but do you have preferred acceptance ratios you would like for these birth and dead moves?
First of all, well, you're trying to. You might. It's very hard to say because you might never have acceptance of one of the model. If one model is clearly preferred over others, you won't see it. What you can do, and again, it's very advisable. You can do parallel tempering as well. High temperature chains will be much more easier switch between different models, because it's kind of equates a little bit likelihood of each of these models, and therefore it will start jumping much more. And then it will propagate this.
Yeah. Okay, thank you.
But you might end up that model 1 never accepted if there is no glitch there. I want to introduce Gibbs sampling because I will need it for later on. I'm again moving away a bit from the transdimensional and base factor estimation. It's yet another technique of doing sampling. It's alternative to Metropolis Hastings. Even though not always alternative, you might have Metropolis Hastings inside the Gibbs. But Gibbs is very convenient in a multidimensional parameter space. And why I'm introducing it, because in transdimensional way, it's also quite often we could use this Gibbs approach. I'm going back to posterior likelihood, prior. Now I will do updates, not all parameters at the same time. But I split my parameters into blocks, B blocks. It could be one parameter at a time, or it could be, n parameters here, n parameters there, etc., etc. Try to split them into the blocks where parameters are correlated. If you know how, if you know by physical reason that this set of parameters should be correlated and other set of parameters are not, split into groups. And make a jump or propose not in all of them, but only in a particular group. So, classical Gibbs basically tells you, you compute the probability of a particular block B, where you exclude this block B from here, and based on other parameters. And actually, quite often, you can see that this probability is analytic. So it's not analytic for all parameters, but for the given set of parameters, keeping other fixed, could be analytic. And then you can simply draw the point without any Metropolis Hastings. I'll show you example later. If it is not analytic, you still can use Metropolis Hastings to draw the point using Metropolis Hastings acceptance ratio from a conditional now. It's a conditional probability, right? It's kind of probability of a particular parameter, set of parameters based on others. And so you're doing the systematic scan. You start with a set of parameters 1. You propose t plus 1 based on previous point and other parameters kept at previous state. Then you go to theta 2. Now you replace theta 1 with whatever you accepted here. And you do so on and so on. So basically, you're cycling along the blocks of parameters. You keep other fixed. You draw the first block. Then you go for second block, but you replaced your first one with whatever you accepted, etc. Okay. So you're not proposing and jumping in all parameters at the same time, but you're proposing and jumping in a block of parameters one at a time, and keep it updated. Why is it convenient? Because it's reducing your dimensionality. Lower dimensional problem is always better than higher dimensional space. So, but the key point here, it's most efficient when you're trying to do uncorrelated. So what you're doing is basically this. Let me draw you. Imagine that you have two parameters, theta 1 and theta 2. And that's what you want to sample, okay? You go in one direction, you go in another direction. You go in one direction, you go in another, etc., okay? When it's ellipse, and especially elongated ellipse, very squeezed, it's not a good thing to do. You either draw in, reparameterize yourself and go in eigen directions, or even better, reparameterize it so it's circle, uncorrelated. And then this one is perfectly working very well, okay? Because here you will often hit the boundaries. Okay, now I told you about the Gibbs and I told you about reversible jump. I want to say a few words about product space. It's another way of estimating Bayes factor between different models. The difference between reversible jump, I'm not doing it dynamically anymore. I'm taking all the models which I want to explore and build one big hyper model with the parameters, basically union of parameters of all signals. If it's nested model, I don't need to do that. I can keep parameters common, to be the same, and just add those which do not exist, but it's up to you how to do it. The idea here is you have from just huge dimensionality of parameter space, and you have order of your models in there. And then you don't need too much any dimensionality. You simply now jump in this hyper model. In practice, how it's done, you introduce the state vector of your M models. So each of the M corresponds to a particular model. Each particular model has a vector of parameters. Okay, so this is my mega hyper model, and the hyperparameters are a product of all of them, concatenated big array. And my M state, either 0 or 1. So it's either model is on or off. And then my product space is very trivial. This is, again, I'm trying to get a posterior on M, model state, and on its parameters. You have likelihood, you have prior on M, and prior on theta given M. And prior on theta given M now is given by this. So where M is active, it's on. Where M is passive is this one. What is this P prime? It's a pseudo prior. In a way, it's a kind of Q, which we used before in the products and reversible jumps. It's some functions which is completely in your hands. If model does not have these parameters, you need to substitute these parameters with something you want to invent. So that's what it is. Your priors has to be complete across all the models. Now you have hypermodel, okay? If a model contains these parameters, you are using them. If it doesn't, you replace it with your P prime. Okay? But you must now formulate prior for all parameters for all models. For those which are active, you're using actual prior. For those which are not active, you use pseudo prior, which is completely in your hands. Is it clear? And your likelihood is works on only active state. So it's data minus mi times h. Mi is either 0 or 1. So the models which are active will contribute to your likelihood. The models which are off, 0, just likelihood doesn't know anything about them. Okay? So first you need to introduce pseudo prior. It could be prior from other extended models, if you wish, and usually that's what is done. Or it's some other function if you have some information to make it more efficient. And you compute likelihood based on only active states. So you transdimensional jump, it's a jump in M and theta. You're switching on and off your models. And I'll just give you state change. So basically when you're switching M, particular M. So it's a priors of each M, of each model. Likelihood which I formulated when M, particular M on and off, like before. And here it's boils down to ratio of your prior to pseudo prior. And again, how do you choose this pseudo prior? It's absolutely the same story which we just discussed for 10 minutes here. So now instead of Q, you will have pseudo prior. To me, it's conceptually a bit easier to understand because when you have hypermodel, if some parameters are not active in this model, I need to choose something for them. At the end, it doesn't play any role in the likelihood. Okay. And here it's very interesting. So do I have an example? Yes, I have example of this. Okay. Again, two nested models, one with theta and theta psi. Let's look again from the product space point of view. Now I need to add two pseudo prior and rewinding a bit. I have two models, and I also introduce this model index k, which is plays role now of my m. So when k equals 0, I'm using model 0. Where k equal 1, I'm using model 1. Okay, it's additional that way. That's my hyperarray of parameters. K, 0 or 1. It means model 0 or model 1. Where does it used? Where is it used? In likelihood. Okay. Then psi are common, and theta are common parameters, and psi is a new parameters. My prior, where k equals 0, are only priors of this one. Okay, and pseudo priors, because it did not exist here. Where k equal 1, that's a physical prior, and I already started factorize it right away. Okay, and you can, and then I will do the Gibbs. That's why I introduced it. First, let's say jump in. I start with the model 0. Okay, I jumped in theta, and no, rewinding again. I start with the. I'm choosing just some parameters, psi and theta, so initial points, okay, in here. And I want to first jump in k. And then I will jump in theta, and then I'm jumping in psi like in a Gibbs way. You remember I said I have blocks, I will jump, make update one at a time. So first I'm jumping in k. And you can show that actually probability of jumping in k is this one. This log probability, log ratio of this. And you can show that actually it's this conditional probability is followed with Bernoulli distribution. So this is one of the rare cases where actually this is analytic. And basically you choose a model with, let me see this, with k equal 1 with probability equal to Bernoulli, which is evaluated at the sigmoid of this LR. So it's nice because you see a really analytic expression for the conditional probability. You don't need to do any Metropolis Hastings key at all. You compute this LR. You substitute this in the Bernoulli distribution, and whether you're choosing or not, certain probability. Next step, you want to jump in the parameters, let's say theta, and you can do Metropolis Hastings jump inside the theta. And then you want to jump in the psi. And jump in psi is either you're drawing from your pseudo prior or you use a certain one. So if you're drawing, so if your k equal 1 after first step, then you need to draw theta and psi based from the model 1. If your k equals 0, so model which does not anything about psi, you're still making update using Metropolis Hastings in theta, and then you draw psi from your pseudo prior. Again, the penalty is how you choose this pseudo prior. I do have some time. We don't, okay, very quickly. Global fit in Lisa. Extremely quickly. We have already everything what we need. We're basically using block Gibbs updates on the different set of populations. So we split populations into the noise, galactic binaries, massive black holes, MRIs, and others. We assume that they don't talk too much to each other. And then we're doing these Gibbs updates. So we start with the noise. we update parameters of the noise, keeping all other parameters fixed, all other sources. We updated noise. Then we're starting, let's say, with the galactic binaries, and we're updating parameters of galactic binaries, keeping everything else fixed, etc., etc., etc. That is all. So that's the basic concept. When you see the wheel, people drawing, it's what we're actually doing. Of course, there are details. So what does it mean, drawing parameters in a noise, given these ones? It basically means that we're taking data, we subtract all the signals of all the parameters, all the signals here, with the fixed parameters, whatever was initial state, okay? What this means, now I'm keeping noise parameters fixed. I subtract everything but galactic binaries. So I'm subtracting massive black holes, etc., but keeping galactic binaries intact. I'm jumping in the parameters of galactic binaries. Basically, I'm sampling only this part, keeping everything else subtracted, and keeping parameters of the noise fixed, etc., etc. So one more thing is, as I said, we have to jump in galactic binaries, but there are many of them. But they're narrow band, so this is frequency, and there is some kind of galactic binaries in these frequencies. You can subsplit your full frequency band into small bands, and you can jump in this band and this band, let's say every even band, independently, because signal really contained within this band, and it might leak a little bit in the neighbor, but definitely it does not affect 0, 1, 2. So 0 and 2 bands, they don't talk to each other, because signal confined into the zeros band, maybe a little bit in 1. So then, in this case, 0, 2, 4, etc., you can run in parallel. 1, 3, 5, etc., you can also run in parallel. The only part which is really has to be, yes, it's a noise. And non-stationary noise, I already talked to you about this. One of the examples of the glitch is this one. And the important part, we already tried to explain to you how to do it signal plus glitch. An example of reversible jump or product space is that you need to feed this data together. The most important, you do not trying to get to feed a signal and then glitch, or glitch and then signal, because they might talk to each other. You want to build a model which contains signal plus glitch and compare it to the model with signal only. This is exceptionally large glitch, and another way of dealing with this, it's gating. You remove this, just throw away this data. That's easy, and if you think your problem is solved there, you are mistaken. Okay, Monsieur Cantat tells me to stop. Thank you very much to all of you. To being with me and to being patient, and I saw your reaction. It's nice. It's really, thank you.
So let's go for lunch. But Steph will be around.
Yes, I'm still around.